Okay, so I will put this in presentation mode so that the still can see it.
Yes, it's good.
It's good. Okay, so I'll start the meeting, and so my name is Jing Wang. I'm part of this CSSI scientific team. So that so I'm welcoming you, and so here, to our workshop, and so I give a very brief introduction to this workshop. So you'll hear that the special thank to Joe, who put the so many hours into getting this workshop together. So speaking of the grazing incident XPCS, let's start with grazing incident scattering for surface structure investigation. So basically, this grazing incident method can explore the structure and the dynamics of a I wouldn't say low dimensional, maybe planar mesoscale heterogeneous systems at the surface, so that and they're all in this 3D. So recognizing the powerfulness of this method, we've been using the grazing incident small angle scattering and or wide angle scattering to study the surface structures like in the energy production systems, and for a lot of system with a self-sampling and the thin film quantum dots and all these things that happening at the surface and the interfaces. The reason we really liked it is that so by changing the incident angle and exit angle, so now we use so in the old days Sunny working in the Sunny's group, so we're doing rocking scans or in the different directions with the point detectors, basically so now we always do it with area detector so that we can see a lot more in the reciprocal space, so that here so that we can see the QX, QY, QZ component, where you can have depth sensitivities by varying the incident angles and exit angles, so that to see all these information, so that so recognize the powerfulness of that method. So I was among the first the team implement this GISAXS beamline at the 8IDE station about 20 years ago. So over the last 20 years, so the GISAXS beamline at the or GIWAXS beamline at the at the 8IDE evolved into and stay to be the state of art, and being very high productive, heavily engaged the research community with in very very broad areas. So but as we started it from beginning, so this beamline was never designed for coherent scattering, so that but rather 8IDI had been for the dedicated XPCS beamline, so for coherent scattering. So so in July, August time period, so you all know that the sector 8 went down offline, and so you'll see that within a few days, so both beamlines become became empty hutches, and then actually hutches now was decommissioned, and now the new hutches are coming up. So the story is that CSSI beamline 9ID will be built for APS-U as an APS-U featured beamline. So this CSSI stands for coherent surface scattering imaging. So it's a dedicated GI coherent scattering beamline. So having the capabilities of doing static imaging experiment, and as well, with the we can do Grazing-incidence XPCS, looking at the dynamics, which is the focus of this workshop, and that's why we are here. So Joe is going to give a very detailed description, introduction to this new, this instrument, GISAXS instrument at the new beamline, and so I'm not going to spend too much time on describing what the beamline is, but the goal is here, with enough sample detector distance and also dedicated, coherent preserving optics, and we can do the GI-XPCS in a much better, or in a much dedicated setup, so that to optimize all the parameters, for dynamics studies. So Joe is going to talk about this more after Sunny's talk. Okay. So one thing I want to just draw your attention to it is, how do we get this large sample detector distance? And you will see here, this whole beamline didn't look like doesn't look like some conventional beamline. You'll see this, that's big. Instead of having a very, very long hutch, and we got this, we designed this with a very large tube, it's a vacuum tube where the detector is sitting in there, so that it can move, so the detectors can move, downstream, upstream, downstream, and also inboard, outboard, and going up and down, so that to collect the scattering from different in different areas of the reciprocal space, so that so what the next movie is showing how big this tube is in in the reality, so that is a tube that this is one of the sections, the 4 sections, so that you'll see this is in the our vendor, so that so there's a about 3 meter diameter, and so total is going to be 20 meter long, and they're going to be installed here at the sector 9 in August and September times. Okay, so what can we do here, with this giant tube and the state-of-art beamline, so that so a few things like surface the dynamics during the surface deposition and the corrosions. And so here, Carl, you'll be, this is straight out of your paper. And also you'll see here is that we took GISAXS patterns, and you will see these roughness, surface roughness related speckle patterns. And so those things will be indicative to the surface roughness process, roughening process, at these thin film surfaces. And those thin films can be also softer matter, so the polymers, and in a broad 2D films, or there could be 3D with these features, and so that you can see the dynamics with the GI-XPCS, and also so that in the air, this is a liquid solid interface, where you can see the biomembranes and the supermolecules in the aqueous environment. So so with this state of art capabilities, that so there are also challenges, and so we're looking at this also to find the solutions, so that this GISAXS geometry, reflection geometry, give us a lot of opportunities, so to look at the heterogeneous structures, and so that the anisotropic dynamics in the films, and so also it brought some complications, such as the dynamic scatterings in the strong scattering Q ranges. So I believe Sunny is gonna tell us all about these things, and I believe the Sunny would, I wouldn't spoil this, and Sunny would tell us don't not too much worry about it. So also this is for wider angle scattering, we should still consider the effect of longitudinal coherence, or lack of longitudinal coherence, with the conventional monochromators, so that the so there are also a lot of opportunities to understand dynamics in this hierarchical mesoscopic structures, and so a lot of simulations and theory needs to be explored to see what we measure and how do we do that, and so that which requires very much of a simulation and theoretical work. So also this high coherent flux that the new APS source provide us opportunity to study fast dynamics or time resolved Grazing-incidence XPCS during the processing, so like spin coatings and all these very fast events, so that so all these things can be explored, right? So, but also it's a challenge that to implement these techniques. Okay, so I wouldn't dwell too much to this, and so again, welcome to this today's session, and so next will be speaker will be Sunny, and Sunny is a professor or emeritus professor at the UC San Diego. So he's been my mentor for how many years? Many since 90s, and so he is a pioneer of the coherent scattering and surface scattering also, right? So that the 84 paper on the dynamic scattering at the interfaces, and so I think Sunny is going to tell us everything, about the, all the questions and opportunities with the XPCS at the Grazing-incidence. Sunny?
Thank you, Jen, for that introduction. So let me, I guess I should start sharing my screen here, right?
Right, let me try to unshare my screen. Okay.
Okay. Okay. Now, the first thing I'm going to do is start things off with a little bit of a bang. I'll show you a dynamical speckle pattern we got at the NSLS.
Excuse me, Sunny, we're not seeing your slide yet.
Oh, just a minute. Okay. Can you see it now?
Not yet. Oh, it's starting. Yes.
Okay. Let's see.
Yes, we see the movie.
Let me try to run the movie again. Let me run it back. Hold on. So this was you could say that's a nuclear explosion, or it's a dynamical speckle pattern from the surface of a spin glass taken at Brookhaven. And this was at Grazing-incidence, trying to do XPCS on that. And we never did understand what was going on here. And nobody at Brookhaven did either. And if anybody can give me an explanation for this, for what's going on with the speckle pattern, I will give you $50. How's that? Look at it once again. Anyway, I'll come back to this later. Okay,
So
now,
that's
what?
a function of a time?
Yes.
Okay, so at a fixed incident angle.
Yes, in real time on the detector, right.
Wow.
Okay, enough of that. Now let me just try to show you my actual talk. Okay, sorry.
Sonny, that's a lot of speckles on your desktop.
Can you see my talk?
Yes.
I can't get it in PowerPoint mode somehow. Let me see why not. Okay, now can you see it? All right.
Yes, it's in presentation mode. Yes.
Okay, so I wanted to thank the organizers, particularly Joe and Zhang and Jin for inviting me to this workshop. Grazing-incidence XPCS brings back a lot of memories because these were some of the earliest experiments that we did at APS when it really got going. It was one of the things I always wanted to do was to study, surface dynamics using XPCS, and finally, when APS came along, we were able to do it. Unfortunately, we were not the very first people. I thought we were the very first people to do Grazing-incidence XPCS, actually. But it turns out we were not, because it turns out we were beaten by our friends in Germany, Metin Tolan and company, who did a study of the surface fluctuations, capillary fluctuations in glycerol slowing it down by going down to low temperatures. So it was very, very slow motion. They were able to do XPCS studies on that. And they did this 2 years before us, they published 2 years exactly before we published our work from APS. Our work was concerned with polymers and polymer films and liquid polymer films. But I should point out that in 1994, as you can see from the bottom reference here, there was a paper from Argonne about observation of X-ray speckled by coherent scattering at Grazing-incidence, although nobody attempted at that time to do any XPCS. It was just showing that you can get speckle. This was the early days. Well, Metin Tolan went on to become president of the University of Göttingen, one of the top universities in Germany. So I guess it pays to be the first to do these kinds of experiments. And here I am. But I'll tell you one thing, there's one thing I'm very thankful for, is never having to be a university president. Anyway, to carry on, I wanted to, before I ran out of time, to express my thanks to people who really have contributed so much to my efforts in this field from the earliest days. And I've listed some of them here. It's not all of them, of course, but these are the ones that immediately come to mind. Suresh, Hanjung, Zhang, Jin, Jots, I don't know what happened. Jyotsna, Metin Tolan, Larry Lurio, Sujoy Roy, Mrinmoy Mukhopadhyay, and many, many others. So right now, I would like to thank them for their expertise and collaboration. I'd like to thank them for the many things I've learned from them. And above all, I'd like to thank them for their friendship. So to those people who might be tuning in who are not completely familiar with photon correlation spectroscopy, when you have a coherent beam, excuse me, of photons, X-ray photons or light photons, it doesn't matter, you get what's called a speckle pattern due to the random interference of the phases from the scattering objects in the sample. And this speckle pattern is shown here on the right-hand side from a static silica glass, which has got a lot of disorder in it, so it produces a lot of speckle. A crystal, of course, would only produce a perfect crystal would produce no speckle, but just Bragg spots. Now, as these objects move around, the phase relations change, and so the speckle pattern fluctuates. And if you put a small area detector, if you put look at a small region of an area detector, you will see the intensity fluctuating up and down in that small area due to the speckles fluctuating in and out of that area. And if it turns out that if you can do the autocorrelation function of that intensity correlated with itself at a later time, t plus tau, then this gives you a function of tau, which is purely a function of the dynamics of the system that you're studying. In fact, it's the intermediate scattering function, or the Fourier transform of S of Q and omega in time at that particular Q vector that you've selected for your little window. And if it's a simple exponential that's relaxing in the sample, then what you get is the modulus squared of that exponential. So you measure the modulus squared of the intermediate scattering function. Now, this is based, of course, on a thing called the Seagut relationship, which says that G2 QT, the function that you measure as a function of Q and time, the time distance, the difference between the two channels is 1 plus B1, the modulus G1 QT squared. That's actually rigorously only valid for Gaussian fluctuations. So if you had, for instance, phonon fluctuations, pure phonon fluctuations, that would satisfy the kind of scheme that you need to produce the Siegert relationship. But you have to remember that when you're doing X-ray scattering, you're looking at the diffuse scattering from the X-rays. And so you're looking at this quantity here. I'm just taking it from you're looking at this quantity correlated with itself at a later time. And you can see that the height correlation function, the thing that's fluctuating with time, is up in this exponential here. So it's not obvious. On the face of it, you wouldn't think that the Siegert relationship would be valid. But it turns out that what people do is you can do sort of an expansion of this. The constant term leads to specular, and the first order term leads to a simple height correlation function, which is a Gaussian fluctuation, and then higher order terms and so on. So in that sense, probably the dominant term, the Siegert relation, is valid, and we don't have to worry about it too much, at least for capillary wave fluctuations on a surface. There may be other kinds of fluctuations at surfaces, for instance, magnetic fluctuations and things like that that don't obey this, and one has to be a bit careful. I just wanted to point that out at this stage. Okay, the other thing that Grazing-incidence XPCS requires is there should be no QZ dependence to the dynamics. Because if there's any QZ dependence to the dynamics, then you know that because of the reflection from the substrate, you're picking up several different QZs at once, according to the DWBA. And so it becomes a bit of a problem to unscramble all that and get the dynamics at a particular QZ. But for instance, particles moving out of the plane of the film in the Z direction would not be suitable for studying with Grazing-incidence XPCS. And QZ-dependent phenomenon, three-dimensionally dependent phenomenon, Z-dependent dynamics would not be suitable to study because of this. Also, if you've got particles on a liquid substrate or at a liquid-liquid interface, then the dynamics of the substrate itself presents some issues that you have to take into account, because now you've got the dynamics of a coupled system, and both of them have to be calculated and analyzed. So, the first experiment that we did, we were sort of oblivious to these issues because we were looking at polystyrene, the fruit fly of polymers on a liquid film on a silicon substrate, and there was none of these issues involved. And let me just say that the only reason why you would do Grazing-incidence XPCS is if you're somehow doing want to look at a film on a substrate, because otherwise, presumably, you would want to do the XPCS in transmission geometry. If you want to do it in grazing incidence and still do XPCS, it has to be because it has to be on a substrate somehow, or a thin film, or some kind of magnetic film on a substrate. In any case, this was the first polymer film that we looked at, and we were very gratified to see that the G2 function became faster and faster as the in-plane Q became larger and larger. as you might have expected it to be. And one thing that I think that one of our contributions in this paper was actually to present a formula for the relating the Q dependence of the relaxation time for a viscous film, a thin viscous film on a substrate. Now, Jack Lee had done a theory in 1998, a full formal theory where he'd introduced a response function and left it at that in terms of a complicated expression. That didn't help experimentalists very much, right? So what you wanted to do was to take his expression and show that it led to a simple formula for the relaxation time as a function of Q and the viscosity and so on. And taking Jack Lee's expression, we were able to get such a formula, which has now been used by a lot of people working on capillary waves and polymer films. It's a way of measuring the viscosity of a thin film if other techniques are not suitable. It showed that the relaxation time over the thickness of the film was related to the ratio of the viscosity to the surface tension times this universal scaling function of the wave vector times the dimensionless wave vector times the thickness of the film, where this function was this series of sines and coshes over here. And this worked very well because you can see that if you take, for instance, polystyrene at 123K molecular weight, at different temperatures, it has different viscosities, but at different thicknesses, all of them scale and fall on the same universal curve if you plot tau over H versus QH. So the scaling relation was demonstrated very well. And here it is again. And you can see that the agreement with the bulk viscosity is measured by other techniques, standard techniques, is not bad. And then, oops, going backwards. And then we showed that for very thin films, when you get down to polymer radius of gyration of RG, the thickness becomes of the order of RG or even twice RG, then viscoelastic effects come into play. And Zhang did some calculations, Zhang did, which showed that you can fit it with a viscoelastic or basically Maxwell model. You can fit the G2 functions, and that for when the film becomes, the thickness becomes equal to RG, there's almost no dynamics. It's essentially static. How much time do I have left, Jin? I can't hear you.
I'd say about 15 minutes.
Okay, thank you. Oh, Joe, you're the chair, right? Okay.
Either way.
Thank you. Okay, so moving on. So this is a viscoelastic model, and one could show that that for two films, basically of the same thickness, but different molecular weights, so that the thickness was 4 Rg in one case and 2 Rg in another case. In the 4 Rg case, the simple viscous model fitted beautifully, the one that I showed you before, involving just the viscosity and the surface tension. Whereas in the 2 Rg case, you needed to use the shear modulus as well, due to having to use viscoelastic effects. You had to introduce a shear modulus mu. And then there was this controversy for a long time about whether there should be, because thin films of polymer showed a reduced glass transition temperature, whether there should be a reduced viscosity at the surface of a polymer film due to the fact that you have all these open loops and endings of loops at the free surface. And we tried to fit a low viscosity surface model to our data, but we were not able to. It didn't fit at all well. But then later on, we did an experiment with Koga at APS, where it was a very clever experiment. It did the following thing. Sorry. It put gold particles into functionalized gold particles into polystyrene, and then looked at the thin film at different angles of grazing incidence, one of which excited a pattern which produced just a broad maximum in the middle and nothing at the top surface and bottom surface, and one of which produced intensity. This is the electric field intensity plotted here at the ends. So if you use one angle of incidence, you would be probing the dynamics of the gold particles in the middle of the film. If you used the other angle of incidence, you'd be probing the dynamics of the gold particles at the surface. And in fact, we showed that the diffusion constant at the surface was quite a bit less than, quite a bit greater than the diffusion constant in the bulk of the film. And even though actually we also showed that the glass transitions were not that different, but this is an intrinsic property of the film, that the viscosity at the surface is less, or at least the diffusion particles diffuse faster at the surface. Okay. Then we studied what happens when the polystyrene film approaches the glass transition. And that was kind of interesting because I'll just go through it very quickly. As you start off at high temperatures, it behaves like a normal relaxation with a simple exponential relaxation given by simple viscous theory. Then as you go down towards the glass transition, you get this anomalous behavior, and you can't fit it with a simple exponential anymore. It has to be stretched exponential. And then when you go down very close to the glass transition, it becomes a simple exponential once again. And this time with an enormously greater mobility, right? And so this was very strange, although not so strange when you think about it, because what happens is, whoops. Is that there's a thing called the entanglement molecular weight for polystyrene, right? And when it approaches the glass transition, you get these series of blobs, which are the entangled blobs of polystyrene. And within these blobs, you get this diffusion, and so after the molecular weight becomes bigger than that, it's as if you were just studying the motion inside these blobs, not in the whole big macro chain at all. And to the polymer physicists, that was obvious. Okay. And then there's work we did with Jyotsna Lal and her students on sorry about that, on a two-layer film, polystyrene and polybromostyrene. Larry Lurio was also very much involved in these experiments, and we showed we were able to do the calculation for the two modes that would exist here. And you can change the angle of incidence and probe the modes at the top, at the interface, and at the bottom. And we were able to show that you could map out the G2 functions for both modes, both for a homogeneous film and for the bilayer film. And we were also able to show that that it could also be pretty well reproduced by like a slipping at the polybromostyrene being static and the polystyrene just slipping across the interface. Okay. Now, one thing I wanted to, this is not a Grazing-incidence XPCS experiment, but it's an experiment we did recently at APS over a long series of runs on a battery electrolyte. This was done with, well, actually, it was really done by Hans Steinruck and Chris Takash, who came, and in Mike Tony's group, and us, and the Argonne group did a lot of the interpretation. Now, I bring this up only to point out the following thing. When you're talking about particles diffusing in a film, we think it's obvious that we're seeing the particles diffusing in the film, but we may not be seeing the particles diffusing in the film. In fact, in this case, we showed that what we were really seeing was the density fluctuations of the polymer around the particles relaxing after the particles had moved, because the particles themselves were too small and weak to scatter. And it was the electrolyte in the film that relaxed as the ions went through, that we were looking at the dynamics of. So a lot of these things where you see things that are apparently got a uniform ballistic velocity through the film, we have to examine very carefully whether that's actually the particle moving or whether there's some other kind of density fluctuation that's associated with it, that's moving. Okay. Here's and this is for the first time a magnetic experiment with XPCS and Grazing-incidence. This is a dysprosium film. We're looking at the fluctuations of the speckles above the nail temperature of the spiral phase. It has a spiral, it goes from a paramagnetic phase to a spiral phase. And you can see that as you go down in temperature, the dynamics of the speckles, as you go up in temperature, you can see the dynamics of the speckles in a more pronounced way. And we were able to fit this with a stressed exponential with a beta of 3/2. Beta of 3/2 seems to be pop up, I don't know why, but mysteriously almost everywhere when you have jammed systems. And we made the claim that this was a jammed system because the domains that were fluctuating were growing in size, and then eventually they jammed together, and the domain wall motion will follow the jammed motion after that. That was our interpretation of this experiment. And this showed that it could be fitted with a stressed exponential and a Volcker, Fourier-Volcker expression for the temperature dependence. And then finally, so now let me make some general remarks before I finish. I'm almost at the end. Can you look at ferromagnetic fluctuations in thin films? Well, one would have to separate magnetic and charge scattering, and you can do this with circular polarization with an I+ and an I-. Now, the magnetic scattering heterodynes with the static charge scattering. So actually, even a weak ferromagnet, because the charge scattering is so strong, you can get a rather big signal in I plus minus I minus. And you can obtain f of qt and not just a modulus f of qt squared. But for slow fluctuations, fast flipping is necessary. Otherwise, you're looking at I plus and I minus at effectively different times. You have to flip very fast and look at slow fluctuations. The other thing that I learned doing experiments at APS, we did some experiments with Suresh on gold nanoparticles moving in multilayers of lipid multilayers. And they move in the plane, and they move quite fast, almost ballistically, or at least fast diffusion. And to measure these fast in-plane motions, you need to really measure down to very small times. We were not able to do this at APS very easily at that setup on sector 8, but we tried to compensate by going to small q, where the motion is supposed to slow down, and we could make the times large enough so that we could measure them. But I think in general, one needs to go to some method of doing grazing-incidence XPCS at very fast times. And one might consider these two pulse methods that they've developed at Stanford or with the mirrors and so forth. So I'll just throw that out and leave that as a possibility of whether one can do that at APS, eventually looking at very fast in-plane motions with grazing-incidence XPCS. And I think that's all I have to say. So thank you very much, and I'm happy to take any questions.
Do we have a quick question for Professor Sinha? I see Carl has his hand up. Carl, would you like to unmute and ask your question?
Oh, no, those were clapping hands.
Oh, sorry, clapping hands.
Okay, thank you.
We do have a discussion period after the next talk.
Okay.
Oh, sorry, Eric has a question.
Just, hi, Sunny, very nice talk. How fast are you talking about for this last bullet that you mentioned with Suresh?
Nanoseconds.
Oh, okay. Okay.
Well, milliseconds anyway.
All right.
That would give you a very comfortable range to look at.
All right.
Okay. Well, thank you. We will have more time for discussion, and I guess after this talk, which I guess I'll start. Let me share my screen. I hope you all can see that.
Not yet, Joe.
Great, thank you.
Not
So,
yet.
oh,
Sorry. Just your Zoom browser. Yeah, no, it's there.
yes, okay, and in
Yeah,
presentation mode.
Yeah,
okay,
looks good.
thanks, Suresh.
Yeah.
Okay, so I'll be thank you. I'd like to give you an overview of our new beamline at 9ID. After that great intro that from Jin and from Sunny setting the stage for GI-XPCS studies. And I'm very happy to have been working to bring the new beamline at 9ID into reality, together with the co-leads on the co-scientific leads on the project, my colleagues Zhang and Jin. But of course, this is actually part of even a much larger team involved. And that includes our whole engineering team, Dana Althoff, Deming, Jason. Jason's been doing the design work, and Ray's been really instrumental on a number of lots of details. Then the optics team, Jean-Beau, Luca, Jonathan, and Sunil with the radiation calculations. And then again, Jin, Zhang, and Suresh rounding out our scientific team and really the glue holding this project together. I wanted to start with just a provocative or bring to your attention an experiment that I think kind of illustrates the need for this instrument. So at 8ID, we've been measuring grazing incidence, X-ray scattering, both in the small and wide angle regime. And this experiment is from Jonathan Rivney's group with collaborators at SLAC, including Chris Tkach, that we'll hear from later today. And but there are operando measurements of organic mixed ionic electronic conducting materials really pushes the state of the art of what we can do. And so with the use of a cleverly designed sample chamber, they're able to put a thin film of this ohmiac material in an aqueous environment and apply an electrochemical potential. So these materials are of great interest because since they conduct both ions and electrons, they're perfect for interfacing with biological tissues. So they're under a lot of interest for implantable, wearable biosensors, but also as building blocks for neuromorphic computing and other applications as well. And so with this sample chamber, you could put an ohmiac thin film down, in this case, PDOT, PSS, and measure here our line cuts from the GIWAXS scattering. And you can see that there are significant changes as the sample is, as the material is cycled through the electrochemical potential. And these changes also manifest themselves in the UV-Vis absorption spectroscopy that you see in the middle panel. And on the right, you can see, just as a function of the applied potential, you measure the change in the current in situ. And then this is focusing on that first lamellar peak in the structure, looking at the intensity as a function of time and seeing how the despacing changes as the material is doped and de-doped. And then similar changes can be followed with the absorption spectroscopy. So, this experiment really, as nice as it is, could benefit from higher energy photons, more flux, being able to measure GISAXS and GIWAXS simultaneously, and intriguingly, if we could measure the dynamics. So that's really, I think, kind of one example of what makes us think about a new beamline to help make these kinds of ideas a reality. And Chris is going to give us an update in his talk later today about the progress in this project. This slide shows you an overview of our new beamline that will be built at 9ID. The A station is being retained from the current 990A. Otherwise, we're having new structures built nestled in between 9BM and 10BM down here. So in the overhead, you can see a mini hutch, a D station, and the grand tube that Jin was telling about in his introduction. In the elevation view, you can see, I'll just point out that in the mini hutch, there is a compound refractive lens, a transfocator. At this position, one in the mini hutch and one in the D station before all the instruments. And that's what I'll tell you about next. I'm going to, in this talk, step through the beamline, working my way downstream as the photons fly. And so with those two transfocators, we can see this is the performance we can expect from the new focusing system that we'll have. So we can either use the upstream transfocator and accept the full beam, and then for GISAXS and GIWAXS, we'll be able to focus the beam down to about 30 by 16 microns or so, depending on the energy that we're looking at. Or we can restrict the beam coming in and focus for more suited for the small spot size needed for XPCS. And then we'll be able to achieve a focus of about 3 microns by less than 2 microns in that case. And you can see these are somewhat energy dependent numbers. And then these fluxes are the expected flux at once full operation is achieved. In the early days, well, I think commissioning is going to start out at, I believe, 25 milliamps, and it's going to ramp up with subsequent cycles, 25, 50, 100 milliamps before achieving the full expected 200 milliamps. But even at 1/8 or so, these numbers are going to exceed our current coherent flux at 8 IDE was in the 10 to the 9 range most of the time, or 10 to the 10th on a good day. So you can see these are going to be big increases in the coherent flux. And now staying in the 9 IDD station, looking at the instrument itself, you can see that the Grazing-incidence X-ray scattering diffractometer and the sample environments are migrating from 8 IDE to the new 9 IDD. So we have an emphasis, or here I want to emphasize the continuity of operations. So we'll continue to have the sample positioned horizontally with respect to the lab frame. We're going to be retaining the experimental infrastructure. So this vacuum chamber, versatile vacuum chamber, that was probably the most the result of a very successful PUP investment from Paul Neely and Wei Chen and their group, has benefited the vast majority of users since about 2015. But we're going to be able to expand the Q range and use the setup either for GISAXS or for GIWAXS. So the same chamber with the different top, and with our Polaris detector brought up close. And of course, besides this vacuum chamber, we'll also be using our suite of in situ chambers for spin coating, solvent vapor annealing, humidity control, thermal annealing. So that will all still be available with the new setup. And then improvements that you can expect with the new beamline will be better motion for the GISAXS detector inside this grand tube flight path. Our new beamline will be tunable. Instead of being fixed at 11 keV, we'll be able to access energies from 6 to 25 keV with, as we mentioned, greater coherence and flux of a new GISAXS detector, which will enable what we're here to talk about today, Grazing-incidence XPCS. We'll also have new motion for the GIWAXS detector on this granite table for enhanced stability. And not part of the scope on day one, but already requested through a major item of equipment request, is a new cutout detector so that we can enable simultaneous GISAXS, GIWAXS, but the infrastructure for moving the detector around will already be compatible with that on day one. And I'll also tell you about some new efficiencies we're introducing at the beamline that we hope will help everybody really make the most use out of this new instrument. So the GIWAXS detector motion, the beamline will be capable of simultaneous GISAXS, GIWAXS pending a new detector. We will have this granite table that'll be able to move the near detector, the wide angle detector in and out. Not shown in this rendering is the vacuum path that will complete the connection from the sample chamber to the entrance to the grand tube. But we'll be able to, with a cutout detector, fit that around that vacuum tube. And then different commercial options exist. So either from there's an Eiger style detector that we could get, or from X Spectrum, there'd be a lambda style detector with even smaller pixels and a faster frame rate. So these are our options that we hope to bring to the beamline pending approval of the scope. The grand tube is something that Jin showed, and this is going to allow motion of the GISAXS detector, which you can see here on the carriage, and then in the animation, it's moving back and forth. So there's about a 20-meter the grand tube is about 20 meters in length, and there'll be a servo to move the entire length of the grand tube. There would be an elaborate beam stop system, so users will be able to choose different beam stops of different widths, depending on their experimental needs. And the direct beam is going to be coming down closer to this side of the grand tube. So this illustration is showing you how far the range is for transverse motion. So besides this transverse horizontal motion, there's also vertical motion, so that there's the size of the detector itself, but also we'll be able to move around to capture the scattering at greater resolution further away from the sample as needed. And the closest we'll be able to bring this detector to the sample is going to be about 3 meters from the sample, comparable to what we have now. So on day one, it'll be possible to do comparisons with GISAXS the way it was done at 8IDE and see the results in the new beamline. Our new detector for GISAXS, which is part of the scope and in the process of procurement, is a state-of-the-art detector from Vectrus. It's the Eiger 16M with a very large active area and small pixels, 75 microns. And this frame rate, either 400 frames per second continuous or 550 frames per second in a burst mode, will put us in the range of being able to follow dynamics in the millisecond timescale regime. And this has a very high dynamic range. And we'll have a much faster detector motion, will be good for filling in the gaps between the modules. If that's desirable, of course, doesn't apply for GI-XPCS, which we will be able to use with this detector. And so we'll be able to track dynamics from the millisecond up to about 1,000 seconds or so. So spanning about six decades in time. The angular range that we can get is going to be about a little bit more than 5 degrees vertically and horizontally. So that corresponds to a very wide range in Q, depending on the energy range. And sort of as a benchmark, this is the comparison with what we have at the sample detector distance and the energy that we have today at 8IDE. This will be the span of the Q range in the perpendicular and the in-plane, the out-of-plane and the in-plane directions. And this would be if you were focusing on one quadrant. So if you had the symmetric view, it would be about half that in either direction. So, and then with the tunable energy, there are really opens up a lot of possibilities for optimizing the scattering conditions for your experiment. And then just comparing the speckle with pixel size. So the Eiger is well suited for XPCS. We can expect the speckle size to go delta X to go like the distance to the detector, the wavelength, and the size of the beam, and with the focus about 3 microns. And with the pixel size of 75 microns, you can see that at the minimum distance that we can bring the detector at 3 meters, the pixel size will be well matched, or even the speckle size will even be larger than the pixel for most energies that we see. And intriguingly, even at very close distances, down to around half a meter or so, the speckle size will be something like maybe half as big as the pixel. And then, so looking at that, I just wanted to have one science highlight that was done at 8ID, and Sunny gave us all that wonderful context. So now I can point out that this is from Mark Foster's group, looking at that fruit fly of thin film scattering polystyrene, and here looking at the role of interlayer film. So in this case, the effect of graphene, putting down graphene on the surface. And in that case, then you can see the dynamics for these blue circles is significantly slowed down compared to these films in green, and then at higher temperatures in the other colors. And so putting down a graphene interlayer between the silicon substrate and the polystyrene film really slows things down. Actually, the red one is with comparable thickness to the other colors, and blue one is at 8 times the radius of gyration. And I'll just point out, so molecular dynamic simulations help interpret these results. And so simulating an ensemble of chains and then only highlighting the structure of just a few of these explicitly, you can see that without the graphene film, the chains are able to freely adopt a variety of configurations. But with the graphene layer, there's a much tighter interaction between the styrene rings and the surface. And so that's really hinders the dynamics. And so, in fact, as Simon pointed out earlier, without the interlayer, without the graphene interlayer, there is a difference, a highly viscous layer corresponding to about the radius of gyration. But with the graphene, this highly viscous layer extends much larger, up to almost 8 times the radius of gyration. So, if we had, with the new instrument and the detector for simultaneous GIWAXS, then we should be able to improve on this experiment by also validating the view suggested here by the simulation work, and be able to see the change in mean orientation of the styrene rings. So further validating this view. Efficiencies that we hope to bring to the beamline under development, mostly relevant for GI-XPCS, is we will have a triple beam interferometer that we'll be able to use to speed up alignment, but also to maintain alignment during experiments. So for instance, with in situ measurements, if we're heating the sample, then maintaining the alignment, especially with the small beams, is challenging. So being able to monitor that with optical means will help enable us to do that. Oops, and the robot will mostly aid in boosting throughput and consistency, and can be a gateway for autonomous experiments, but I think that's going to come more into play for GISAXS, GIWAXS. And then probably the most important efficiency that will affect GI-XPCS is that there is already a well-developed infrastructure for XPCS analysis and data reduction already developed at 8IDI and has been in use. And this is going to be boosted with further improvements to data flow rates and tighter connection to high-performance computing resources available here at Argonne. And then, so we'll be adapting that for use at 9ID, and also adapting it further for the grazing-incidence scattering geometry, so that we'll have the better or more complete or the relevant treatment of all the components of the Q vector that are necessary for when the surface comes into play, be able to do line cuts, reshape, and compute pole figures, other things of interest to the GISAXS, GIWAXS community. Okay, and then I'll wrapping up. I can point out to you about the timeline. So as you're aware, 8ID operations shut down both 8IDE and I at the end of July. And now we are just entering the dark period for APS-U while the storage ring is being completed. I can point out that the 8IDI hutch, the new 8ID hutches for the XPCS feature beamline are almost in place. And 9ID constructions on the new 9ID hutches will be next on the installation schedule. And while that's going on, we will be organizing a workshop for first experiments at 9ID, which is scheduled for August 8 and 9. And that's going to take place at the APS, and we're strongly encouraging people to come out for that and participate in person. And that will be ahead of the first proposal call in September. So it's a good time to encourage everyone to be thinking about first experiments on the new beamline, and parenthetically, that should be around when the grand tube is installed. And then we'll be transitioning towards beamline commissioning initially and installation, initially without beam, and then in 2024, we'll be starting a period of commissioning with beam and transitioning towards early experiments in the commissioning period and afterwards. And then, so just in conclusion, I hope I've shown you that we're developing a world-class instrument for dynamics and structure of thin films and surface structures at 9ID. And this will allow a view of dynamics with routine access to the grazing-incidence scattering geometry with a suite of sample environments, a state-of-the-art detector, support for automated data analysis, data reduction. And our staff is ready to work with you for your experiments. It's time to start preparing for that. And this is sort of showing the region where we will be specializing. We should be able to cover this region and hope to extend towards larger Q. I believe that's it for my presentation, and I guess I'll hand things over to Zhang as our discussion leader for the discussion period.
Okay, thank you, Joe, for your beamline introduction. Is there any questions for Joe?
Yeah, I had a question.
Okay, yeah, go ahead.
The question is simply, what's the situation for users being able to bring their own modest chamber and install it?
Yeah, so I think our diffractometer is fairly robust, and I didn't have numbers on there, but I think we can handle a fairly robust chamber, and there should be adequate room for it. So we're willing to work with that and accommodate user sample chambers.
Great, thanks.
And also, Joe, you may want to mention that upstream of your chamber, you have a placeholder, right, for any.
Oh, that's true. There is also a stationary space that's not part of the translation for the sample chamber that I showed. So that could be also a good place to put additional user equipment needed, maybe for auxiliary equipment or for a larger sample chamber.
So Carl, we had you in mind when we reserved that spot. So,
but then one would have to put in something for motion, right?
Right.
Yeah. Yeah, we will have that. So we will arrange for that. So just the chambers.
Looks like Hua has a question.
Yeah, I have a quick question, Joe. For the infratometer, for the look like the position stability. So that setup is only for the GISAXS or for the also the for the CS. I mean the for both, right? For GI-XPCS and also.
No, I'm sorry.
CSSI.
I did not show it except in the overhead view. So what I was showing, what if you can, I'll get the laser pointer on. What I was showing was down here at the very end of the 9ID station, and the CSSI is going to be here upstream. So in fact, there's a KB mirror that we won't be using, that's intended for focusing for the CSSI station, and then the CSSI solid sample station is right here. So that's going to be, pardon?
So I think Hua's question was whether the GISAXS and the GI-XPCS setup was the same. Chamber is the same, right? Hua, is that what you asked?
Well, no, where is the slide?
But were you asking about CSSI and XPCS?
No, not CSI, but the one Joe showed.
Okay, sorry. So in that case, you're right.
Infratometer for the positioning alignment using the the infratometer, right? I think.
In that case, you're right. So we are intending to do GISAXS and GIWAXS and GI-XPCS using the same diffractometer, and so that should promote synergy between being able to measure structure and kinetics and also dynamics on the same system.
Okay, and also there's how quick the response time for the infrarometer for the positioning, because you mentioned about it during the heating things could change or drifting. So how quick the response for that system, the laser system?
I guess it's still under development, but we're envisioning to be, keeping track of that on something like a 10 hertz rate, something like
10
that.
hertz, okay, 0.1 second. Okay,
So,
good. Yeah, that's good to know. I just want to know whether they're only good for, like, for example, slow change, for example, your heat up, because heat ups usually is maybe slow change, or they also can adopt any sudden change or something. So, okay. 10
right.
hertz maybe.
Right. I mean,
Yeah.
I guess with the thermal stages that we have now, so mostly we're relying on a Lincoln stage.
Yeah.
That's from about liquid nitrogen temperatures to about 300 C, and that one heats at about up to about 20 degrees per minute. So
Per minute, yeah,
we think we could potentially keep up with that.
Yeah. Okay. Good.
I think we have Eva has a question.
Thank you for the nice presentation. I was just wanted to make sure in Jin Wang's talk, I understood that the sample is vertical, but it is horizontal. That's the plan, is it? Because Joe, you showed it horizontally.
Right. So GISAXS, GIWAXS, GI-XPCS will be with a horizontal geometry. The CSSI instrument has the sample mounted vertical.
Ah, okay. Then I missed that one. Okay, thank you.
Yeah, I had a comment in my presentation saying GISAXS, GIWAXS retain the
okay, yeah,
vertical
I was just
scattering
quick enough.
Yes. Sorry, that
No worries. So you said that it should be rather robust, but with what do you align the sample? Is it a goniometer or is it a hexapod? And will there be room underneath the sample as well for some space for the setup?
What are we aligning with? I guess right. So we should be able to align. We plan to align the samples using the area detector. Effectively, our counter downstream of the sample is going to be the area detector. So that's what we really hope to align with, although we do plan to develop using the interferometer so that we're hoping that we can steer the sample into position and maintain it there using the interferometer, but ultimately it'll be the area detector that we're using for alignment.
But it will be mounted on a goniometer or on a hexapod?
The sample will be on a goniometer, not on a.
Okay,
So-
because then it's important to know how much space you have underneath if you bring your own setups to still be
I
able
see.
to.
Right. So the working distance on that, I'll say it's about it's more than 200 millimeters if you were to
Okay.
dismount the chamber that's on there now.
Okay, great, thank you.
I guess for example, we take the chamber that I've shown, that vacuum chamber, off and put our in situ spin coater on, and that's fairly large. That's about 200 millimeters to the sample from the base. Then-
Okay, any more questions for Jean or Sunny or Joe?
Maybe one question for Joe, like the center, if there's a mode where you have the 4M, does it improve the speed?
Believe it should. I'm honestly, maybe Suresh knows the details on that better.
I think, yes, that is correct. So the full detector is 400 hertz
And that's the burst
steady
mode.
state and 550 hertz burst mode. And if you use the central 4M ROI, that's 1 kilohertz.
Oh, okay. Maybe it's a little bit more of an internal question. Isn't there another detector for CSSI that's like sort of based on the Cornell
pads, like,
designs?
yes, the analog pixel array detectors, the pad.
Yeah.
So those have like fairly large pixels. I believe, I'm not sure, 150 or 200 micron. Eugene knows about that.
Yeah, these are 150 micron. So these are large pixel size, and these are operated. Intention is to have that detector to see the direct beam without much attenuation. So we have not done anything with that, to do XPCS. We don't know how this thing is going to work with the XPCS.
Is there the possibility of a burst mode?
This one doesn't
No.
have the burst mode.
Yeah, it doesn't give much higher speed. It's only a kilohertz continuous mode.
Okay, so well, so we are always open to discuss or provide more information about the concept of GI-XPCS and about the beamline. If you have more questions beyond what Joe can present in his short time. Yeah, so I want to say something about it. So both Jean and Sunny mentioned that this XPCS is challenging to to the grazing-incident reflection geometry than transmission. I saw the list of the audience in this room, found out that some of them have the grazing-incident experience, but maybe not on the current XPCS, and some has the doing like a static structure measurements, but don't know how to do dynamics probably. And so I want to say that this kind of dynamical effects are expected in a surface geometry. So it's important that we need to understand the origin of the scattering signals, because they are typically more complicated than transmission geometry. And it's not like as simple as we analyze Brownian motion dynamics, like in transmission geometry, and also unlike many image experiments, what you see is what you get, or what you get is what you see. So the moment, in XPCS, at the moment, we see the beautiful multi-tall, or this, this two-time correlation function, that's not the end of the, the data analysis. So that's probably just the beginning of the data analysis. So we have to find out, physics models, to fit or reproduce the correlation functions you get. So this kind of models, I would say, needs to take into account of, two considerations. I think Jim mentioned that, and Sunny also mentioned that. So one is this, this dynamic of the sample itself. The other thing is effects introduced by the Grazing-incidence geometry. For example, this multiple scattering or heterodyne, things. Sunny, mentioned that, I was not fully aware, although I know a little bit, I never fully aware of that. The dynamics, in thin field geometry, it's not easy to measure if, for example, if the magnitude of the motion you are interested in is too large, in the Z direction, normal to the surface. So, but anyway, so what I want to say is, the analysis can be challenging. So, but there are a lot of opportunities there. So we, like Joe said, the beamline staff, we work with you, provide support in planning experiments and in help, analyze the data. So we will work with you. So any comments or questions about this, morning session, Jim's talk, Joe's talk, and Sunny's talk? Okay, Eva, go ahead.
I have a question to Sunil's talk. Thank you very much. I really appreciated this great overview. You mentioned the Z direction within the dynamics that might become a problem. Do you think this is generally a problem, or only why we don't obey the if we're not taking into account the DWBA?
Well, I think if you've got only in plane motion, or if it's a really thin film, I think you'll be okay. If you've got a more three-dimensional system and you've got things that are changing in the Z direction or particles moving in the Z direction, then I think the reflection from the substrate will give you a mix-up of the scattering at different QZs, as we know from the DWBA. And in principle, this can be sorted out, but it takes a more complicated analysis. So I would suggest that if you want us to do those kinds of experiments, you try to do them in transmission, or if they're on a substrate, then presumably there is not much motion or structure in the Z direction, and you're probably okay. I think that's been the case in most of the systems studied so far. I don't know of any systems where the Z direction has been a problem, actually.
Okay, thank you. Maybe we can talk after my presentation tomorrow.
Okay, sure.
So I think, just a little bit of my thought on this is that previously all the GISAXS, GI-XPCS are done trying to avoid the center column, on the detector, near the specular reflection. But because of a lower flux, coherent flux, and so most of experiment are down near the horizon where this Ionida wing is actually. So that's turns out that could be a very complex area where you could mix a lot of the dynamical information in there. So with the higher coherent flux, it'll be possible, so that you have a better intensity, away from those areas. And so that's where probably safe, we can assume, you have less of a contamination, let's say contamination of dynamical scattering in those areas.
Sure, but you might more easily grill your material as well.
That's possible. So that yeah, it's always the trade-off, so that
one thing I wanted to add to Eva, I guess when people are looking at, for instance, capillary waves or things, surface fluctuations, they usually come in at below the critical angle, so that you don't have any reflection from the substrate. So actually, if the beam is mainly reflected from the surface of the film, then I think the DWBA effects will be sort of minimized. The substrate is not reflecting.
Right.
Yeah, so my question was more like, do you think it's a physical constraint of obtaining the right information from the scattering pattern if you're going in, if you have to include the vertical motion, or whether it's simply that we can't cope with the DWBA?
So vertical motion is another thing that one would have to then study the XPCS as a function of QZ, and that of course can be done, but it's usually one only studies as a function of Q parallel, but it can be done. Yeah.
Thank you for your input.
Okay, so I mean, we can have more discussions in the afternoon session and even tomorrow. So if there are no more comments or questions, so let's move to the break time. We're gonna have a 30 minutes break, and we already like 5 minutes past the schedule. So we will come back around 25 minutes. It's a Chicago time 11:45, but I mean, you calculate your own time zone. Okay, so this is a coffee time, and this is probably also a lunch time for a lot of you. So okay, we will come back in 25 minutes. Thank you.
Yep. Bye.
Bye.
Okay, welcome back, everyone. Let me introduce our next speaker. So Carl Ludwig is professor of physics at Boston University, where he also holds an appointment in the Division of Material Science and Engineering. Carl completed his PhD in applied physics at Stanford University and completed a postdoc at the IBM T.J. Watson Research Center before joining the faculty at Boston University. He's been a pioneer in real-time X-ray studies of dynamic processes in inorganic materials and has worked at a variety of light sources, including both synchrotrons and X-ray free electron lasers, including Sector 8ID here at APS. And today, Carl will be telling us about some of his work in a presentation, Coherent X-ray Scattering as a New Tool for Study of Surface Growth and Patterning Dynamics. So please, Carl, the floor is yours.
Thanks, Joe. I guess the one thing you left out is, like everybody else, I'm just getting 1 year older every year. So I changed things up slightly after our discussions here this morning. Oops. All right. So can you see that? Can you see that?
Yes.
Okay. Thank you. So our work in the area has very much been in collaboration with Randy Hedrick's group at Vermont. We got our start in this area working with Suresh and others at 8ID, so thanks very much to them. More recently, we've been going to the NSLS2, CHX, so my thanks to all the good folks there. And we've also been collaborating closely on some of the work with a group at Naval Research Lab. So a lot of people involved. Our goal has really been to develop surface-sensitive XPCS as a tool for investigation of dynamics during surface growth and patterning processes, and really focusing largely on GISAXS geometry. So these are some slides I threw in just to maybe kind of give another perspective of these discussions we've been having this morning. Of course, if we have just a single scattering approximation, the Born approximation, and I'm taking these figures from one of Zhangjiang's talks, then we have, simply the Fourier transform of our sample. But in the grazing-incidence geometry, we have more complicated processes going on, as we typically just try to describe by the distorted wave Born approximation. And in fact, my group has usually been operating in a regime where we decide to go in with an incident angle above the critical angle to get rid of some of this complexity. And if you go in, well above the critical angle, then the reflectivity, coefficient of the incident beam drops off quite rapidly. You get rid of these terms. Of course, if you go to sufficiently high output angle, then you also lose this remaining term, and you're just left with the Born approximation. That's what Jen was kind of referring to this morning. But even if you don't go to such high exit angles, so for instance, if you're looking at the Yoneda wing, so you're going out at the critical angle, you've got these two terms. But if you look at them, so right around the Yoneda wing, if you for simplicity take the reflected coefficient at the critical angle to be 1, what you see is that these terms combine in kind of a nice way, such that you can pull out a exponential term related to the incoming beam, and then you get simply a cosine term due to the sum of these two complex exponentials. And the cosine term involving kz times z, the surface height, to the first order is just 1. And so, of course, you get the kind of well-known factor of 2 coming into play, but you get a very simple expression. So if you just turn to something like a standard program for calculating GISAXS, like GISAXS, And I just put in parameters that were used, for instance, in this paper by Operando et al. 3.8 nanometer diameter truncated platinum spheres on mag oxide. Critical angle is 0.2 degrees. If you go in at 0.4 degrees, and then look at the ratio of what the DWBA predicts compared to just a Born approximation. If you look in QY along the Unida wing, you know, they're very close. They're within 1% or so of each other. This simulation was with no roughness on the surface. If you put in some roughness on the surface, you get a little bit more variation in that ratio across the range of QY, which is the sine 2 theta term. So, you know, as we kind of we're seeing, you know, the variation in plane is not a big deal, especially if you're going in above the critical angle. Here is a plot as a function of QZ for the ratio between the DWBA and the BA. For this case, again, of going in above the critical angle. And of course, there is this big QZ variation, which is exactly what Sunny has been referring to. But at any given QZ, each of the kind of the widths of these blue markers represents effectively the variation in this this ratio as a function of QY, meaning that there's not much variation in QY because it's maybe about a 10% variation. So, you know, we have often found simply going in above the critical angle, you know, can help with interpretation. So that was, I just wanted to kind of put that in there. Okay, going back to my talk, you know, one thing that we like to think about as we imagine the process of looking at growing a film or patterning a film is the difference between kinetics, which we think of as an average evolution of a system that's evolving, you know, in a non-stationary way, versus dynamics, which are fluctuations about the average, which is what, of course, we can do with the XPCS that we could not do with a traditional low coherent scattering experiment. So quickly, I'm just going to mention some work we've been doing in ion beam nanopatterning, some work we've been doing in what I here call imperfect thin film growth, and I'll come back to that, and then opportunities and challenges. So in this ion beam nanopatterning, you know, what this is I call it sometimes the simplest experiment in condensed matter physics. You just take a broad ion beam and you illuminate a surface with it, and depending on parameters such as material, the ions, the energy, the angles, you can have nanopatterning spontaneously occur on the sample. So for instance, this on the left is the spontaneous occurrence of nanoscale ripples on a piece of silicon. On the far right is spontaneous formation of nanodot pattern on gallium antimonide. So it's a very interesting process. You know, what you're doing when you're sending in this ion beam is you're sputter eroding the surface, you're knocking atoms around, but yet out of this very disordered process comes a somewhat ordered situation. And, you know, you'd like to understand that, potentially you'd like to even use that, but there's been a lot of controversy in the field and a lot of competing theories trying to explain why this occurs. So what we do with GISAXS is in particular, is we've been watching as we form these patterns on the surface of silicon and silicon oxide. You know, here on the bottom left shows a typical GISAXS pattern where your Q parallel is down at the bottom, QZ, it reads up, and you've got the central Q parallel equals 0 intensity, but then you've got this intensity along the wings or over on the sides, and this is due to the formation of the correlated ripples during the bombardment, and then the Unida wing is also shown. So what we do then is we watch as we develop these ripples, we measure their evolution and then try to compare it with what different competing theories might predict. So this is low coherence. What can we learn from the XPCS? So if you go and do this experiment with XPCS, you know, here's a typical 2-time correlation function you might get out. which shows increasing correlation times with increasing bombardment time. So again, red is of course the high correlation region, and kind of the width of that correlated region is growing with bombardment time. Structures are becoming longer lived. And then you can, at various times fit those decays with a KWW form, which can give you, of course, a simple exponential relaxation or a compressed or a stretched exponential. Like other groups, we often see not simple exponential. We see other relaxation behavior. And, one of the things we think about, of course, is what that tells us. Now, as I said, there's a lot of theory that's been done in this field. One of the simplest things you can imagine is a linear theory. And here you can also kind of make some larger connections, right? So a linear theory is simply a theory that says that the rate of change of whatever coarse grain parameter you have with time is equal to some function, with the function is linear in that coarse grain order. And again, for this nanopatterning process, that coarse grain order is simply the coarse grain local height, plus some stochastic noise. And the nice thing about anything that's a linear theory, of course, is it can be solved analytically. And in fact, it basically predicts an exponential relaxation. Now, of course, we know that during this patterning process, we have strong nonlinearities that come in. Theorists write down nonlinear theories. And so when we fit our correlation functions, they're not simple exponentials, they're typically something else. As we see those and think about them, it's also useful to think about what these different exponents that come out of a KWW fit actually mean. One important thing to keep in mind is for us, and probably most people in the XPCS field, is when we're fitting a relaxation curve, we're fitting the early part of it, not some late long time behavior. We're fitting an early time behavior. And an interesting thing about a compressed exponential is that it in fact has an infinite slope as it approaches t=0. And it has this kind of curvature upwards, as you see in this figure. It's the blue line. So actually, for times less than the correlation time, a stretched exponential is below a simple exponential. And for a compressed, for a compressed exponential is below the simple exponential. For a compressed oops, I see I have a mistake here. For a stretched exponential is below the simple exponential. For a compressed exponential, that's the gray line here. I really need to fix this slide. And the compressed exponential, is actually above a simple exponential for short decay times. And so it is actually telling you this compressed exponential comes in with a 0 slope. It's telling you that you do not have short relaxation times. And while a stretched exponential can be written as the sum of many relaxation times, that's not possible with the compressed exponential. So, I get into this because when we start fitting these correlation curves, we see a wide behavior of the correlation times as a function of Q parallel. And we also see a variation of these exponential relaxation coefficients, n, powers n. So here is comparison of the GISAXS pattern in the speckle average GISAXS pattern in blue with correlation times in black. And what you see is couple things. First of all, there are peaks in the correlation times at the same wave numbers as you have peaks in the scattering. So peaks in correlation times at the length scales at which you have the ripples forming. You also see that there's some asymmetry here. And that's very believable because this is a pattern that was created by off-axis bombardment of a piece of silicon to form ripples. And so, so having the ion beam come in off-axis breaks the left-right symmetry of the process. This peak behavior where the time scales for relaxation are kind of following the intensity of the overall scattering is very evocative to us of the Jean narrowing in liquids. And the Jean narrowing can really kind of come back to this linear dynamics behavior, which suggests that you should have a simple exponential relaxation. And in fact, that relaxation should be inversely proportional to the structure factor. So that's well-known, behavior in liquids, so it's quite interesting to see that here. However, we do find clear differences than that simple behavior you find in a liquid. Here, it's not a simple proportionality that the correlation time is proportional to the structure factor. You'll see that the intensity scale on the right is a logarithmic scale, whereas the correlation times are on a linear scale. So the correlation times don't vary nearly as much as the intensity of scattering. And now we get to these exponents. And what we see is that while a simple model of the Jean narrowing in a liquid would say we'd have a simple exponential relaxation here, around the length scales associated with the ripple formation, what you have are exponents, in the 1.5 to 2 scale. So, so these are compressed exponents. And as I said before, a compressed exponent means that you do not simply have a combination of many different simple exponentials, and it means that at short length scales, you don't have changes going on. There's persistence in the structure. So we've also used these kinds of results to compare with theory, because the theories are nonlinear. You have to do a simulation and then calculate the predicted behavior, and then you can compare that with what you actually observe. So that was kind of using correlation functions, which is the kind of the first thing we think of when we think of XPCS. However, there are other important things that we can look at. One of the things we'd like to know is what is the velocity of motion of structures across the surface. So when you use this broad ion beam bombardment of a surface to form ripples, not only does it spontaneously form ripples, but those ripples can then move across the surface. And what I've written here is a simple prediction of how fast they should move across the surface based upon variations in the sputter yield Y as a function of the ion bombardment angle theta. And so this V is the velocity that these ripples are expected to move across the surface, but it's been very difficult actually in the field to measure these experimentally. And there have been even disagreements about the direction of the ripple motion, much less whether it obeys this actual formula that theory comes up with. So how can we measure this with XPCS? Of course, if we have these ripples moving homogeneously across the surface, then that just introduces a phase factor, and in homodyne scattering, you would not be sensitive to that phase factor. Fortunately for us, we accidentally applied not a uniform ion beam driving, forming and then driving these ripples across the surface, but we accidentally had a non-uniform beam. And so that was serendipitous, because that breaks this problem. Because if you have a non-uniform ion beam, and we assume that the velocity of the ripples is simply going to be proportional to the ion flux at any given point on the surface, now you've got a gradient in flux and therefore a gradient in velocity. And it's known how a gradient in velocity is going to affect speckle motion. It's going to cause the speckles to move. And sure enough, that's what we saw. This is just a a picture of our sample where the ion beam was coming in from the right, and this was on a piece of SiO2, so you could this SiO2 film on top of silicon, so you can actually see the eroded regions through these interference fringes, and you can see where the X-ray beam was hitting. We took a little line and placed it there. So because of the inhomogeneous ion beam and therefore the inhomogeneous velocity of ripples across the surface, we could, by tracking the speckle position, look systematically at how that varied in QY in the plane, which is what you would expect for simply a gradient in velocity across the surface. But a gradient in ion flux also means a gradient in erosion rate. So we also have a term that depends on QZ. And by looking carefully at this, how the speckles tracked on each side of the detector from plus QY to minus QY, you could figure these things out and figure out the gradient in the erosion rate as well as the gradient in ripple velocity. And putting that together, you get, you could measure an average ripple velocity, which in this case was about just under 5 nanometers per second, and it was in the direction of the ion beam, which was actually the opposite as to what was expected. It could be that the theory has a fundamental problem, or it could be that the problem is the theory relies on derivatives of the sputter yield, and how well is the sputter yield actually known. But we're certainly at the point of testing theory to the extent that you know the parameters going into the theory. Next, I quickly wanted to move on and talk about studies of thin film growth. A couple of the studies we've been involved with. And here, what I want to say when we talk about imperfect thin film growth is that we all know beautiful studies that we can do with low coherence resolution, looking at very perfect thin film growth, right? Where you can look at layer by layer versus step flow, for instance, versus a 3D growth. But most materials that you want in the world do not grow in beautiful layered format. They grow in more complicated morphologies. And I feel that we have a wonderful opportunity here for the coherence of the X-rays to substitute for the missing coherence that occurs in more realistic thin film growth processes. So this first example was one largely driven by Randy Hedrick's group. And as I said, a lot of the focus here is that while low coherence studies can show us a lot, for instance, using anti-Bragg conditions, in reality, most films do not grow so perfectly. So this work was looking at polycrystalline growth of C60 that was thermally evaporated onto a graphene surface. And so the morphology you get is not these beautiful single crystals, it's polycrystalline. However, if you look carefully with AFM at each polycrystal, what you can see are terraces. So so traditional low coherence experiments, would have just averaged over all of this, and we would have been limited in what we could learn. But by using the XPCS, what we see here in the two-time correlation functions is that there was a very repetitive pattern happening. And so despite the complexity of having a polycrystalline material with these steps on the surface, what was happening was that as you deposited material, you were having step flow on each of these terraces so that the surface repeated itself on the nanoscale. And so Randy's group was able to make a simple model of this based on the Zeno model, which just says, as you deposit materials on terraces, short terraces, they don't have too long to grow, but then again, because they're short, they get less material, and it leads to very, very particular kind of morphologies. This is shown as kind of like half of a grain in the polycrystal at the bottom. But they all grow out at the same rate because of that. And that's what leads to this consistent repeating behavior. They were able to do excellent fits of the correlation functions using this kind of model. And as I said, to me, what we're really doing is we're using the spatial coherence of the X-ray beam to substitute for the missing spatial coherence of the growth process. And then this last one I'll mention is work that's still being analyzed. I'll just put this in to say that, now that we had done this with a very ideal case in a way of just thermal evaporation of C60, now we're turning and seeing what can we learn about imperfect thin film growth in a much more sophisticated growth environment. This is work in collaboration with folks at the Naval Research Lab. So this is looking at plasma-enhanced ALD growth of epitaxial indium nitride. Of course, continues to be widespread interest in ALD processes, highly conformal. You can nominally control things at the atomic level. You have these beautiful little cartoons that show the different processes that occur to create individual atomic layers. This was the growth chamber that we had constructed and brought to CHX beamline for these coherent experiments. We had a standard growth cycle, 60-second growth cycle of putting in a precursor, purging, exposing it to a nitrogen plasma to react the indium and the indium precursor, trimethyl indium, and get it to react and create the crystal on the surface, and then a purge, and then all this gets repeated. And despite how beautiful this kind of picture is of the atomic layer deposition process, in fact, this is what the sorts of things we observe in low coherent scattering, is that you get correlation peaks. In fact, you get mounding that occurs. So it's not perfectly conformal from the beginning of the process. So you get spatially correlated mounds formed during atomic layer deposition, and they coarsen during the growth process. So here's, for instance, what a two-time correlation function looks like in this kind of situation. And what you see is a lot of complexity that we're still in the process of analyzing. You see at the early growth times, correlation times are relatively small. If you look closely, you see a blocky kind of behavior, which we believe may be associated with sudden stress relaxation events. And you then around, let's call it 2000 seconds or so, what you see is that the correlation times suddenly grow tremendously. So suddenly the film has become highly conformal in its future growth. And this is about the point at which the substrate is fully covered with the indium nitride film. And also what you see is a lot of fine structures. So there's a periodic structure associated with that growth cycle that we're now analyzing and fitting to simple models. We think we're going to be able to learn a lot about just what's happening in each of the parts of that growth cycle. So I think that this is a very exciting data, but still data analysis is underway. Opportunities and challenges. I think, again, utilizing the high coherence of the X-ray beam, I believe that this gives us opportunities to investigate what I would say real-world complex growth and patterning processes, opportunities to continue to develop studies of epitaxial growth, maybe to incorporate some imaging methods along with the correlation spectroscopy. I think there's also a lot of work to be done, an opportunity to advance our theoretical understanding. For instance, the meaning of these compressed exponents, persistence. Challenges, of course, incorporation of sophisticated growth instrumentation into coherent capable beamlines. And normalization in non-stationary systems is always a big problem for us. And sample damage, of course, is something we have to worry about. So with that, I'll bring it to an end and thank all of my collaborators over the years. Stop share.
Thank you, Carl, for that talk. It was wonderful. We have a minute or so for a question or two, if there are any questions out there in the audience. Please just go ahead and unmute and ask.
I have a question for Carl. Is anybody else up there?
Please go ahead, Sunny.
Okay, very nice talk, Carl. This two-time correlation function you showed at the end, very intriguing. It seems to be, what is the significance of it becoming blocky, like with these square blocks in the two-dimensional plot? Is there some particular pattern of dynamics that corresponds to that?
So, well, that's a $64 question. You know, if we focused more on these early stages, you see it's even stronger there. And again, we think that it could be due to sudden stress relaxation events. You know, we had done some work with martensitic alloys years ago in which you know, you saw a very blocky behavior associated with stress relief events in during the martensitic transformation. You know, we would like to be able to argue that they're a little bit less important as time goes on, but you know, you can see it's complicated.
Yeah, yeah. So it looks like you start off as time goes on, the little blocks become big blocks in this two-dimensional plot, and the whole thing expands. It's just like these little squares in the two-dimensional plot become bigger and bigger in the two-time correlation function. I wonder what that means.
Yeah.
I mean, they're little squares all the way along, and then there becomes one big square.
Well, so certainly you know, the biggest kind of square you can see here is starting from 2000 seconds, right? That's, again, that seems to correlate well with the time at which you have a continuous thin film. So, right, we're growing in a three-dimensional growth mode. And so at earlier times in this, there's still bare, we believe there's still bare substrate around. And so it seems part of the answer here is at that point, we think that we're getting simply much more conformal growth than we were before. But as you can see, and again, the very fine structure you see here is real. That's, I haven't blown this up for you because it's still in data analysis, but the very fine structure is the 60-second cycle. And that you can study that 60-second cycle. I just haven't put the plot here, but you're right. There are other blocky structures that we're struggling with.
Okay.
That is intriguing. I see another hand up, but I think we should probably continue this discussion in the discussion period after our next talk. So I want to invite Chris Takash to get his slides together, and while I give an introduction. So Christopher Takash is a staff scientist at SLAC National Accelerator Laboratory. Before that, he completed his PhD on organic photovoltaics, working with Professor Alan Heeger at UC Santa Barbara, and then completed a postdoc at Stanford. Chris has a keen interest in the function and characterization of organic electronic materials, and he'll be talking about understanding dynamic strain and reversibility on an organic mixed ionic electronic conductor using operando GI-XPCS. So Chris, please, the floor is yours. And we see your slides already.
Great. Well, thanks, Joe. Yeah, so it's really great to be here. Yeah, you know, my work in photon correlation spectroscopy actually kind of goes back to my undergraduate work, where I will just say I wandered into it. I started doing visible light scattering with I think some of the people here may know David Cannell and Marcio Giglio, on a project where we were trying to understand fluctuations in non-equilibrium conditions in microgravity and on Earth, using an instrument that is based off a visible light near-field speckle measurement to measure S of Q and omega. That was flown on the Photon M3 mission back in 2007. But as I'm sure many people here who do XPCS know, the analysis of these things take time, and we're actually still publishing papers coming out of this today, or I should say my former collaborators are. It's been very productive. And especially if you're going to shoot something into space, it's, I would say, a generally good thing. So when I went and did my PhD, I sort of switched topics, or at least I kind of initially thought I did. I went to doing cryo-EM of conjugated polymers, where it turns out mathematically cryo-EM and high-resolution TEM of polymers is mathematically effectively identical to near-field speckle instrumentation, except in real space, where you start to have much higher order correlations in materials spatially that go across scale, and that's what we observe and try to understand. So using that sort of came about with these sort of wavelet decomposition methods to look at these lower order correlations in their locality, and sort of been applying that continuously to different systems today. And I would say that actually was really important when we went back to XPCS. It was actually Sunny who called up Mike Tony and said, hey, we should do something with XPCS. And after a lot of trial and error, we came up with something, and I'm putting XPCS in quotes here, was something where we used a heterodyne measurement to effectively measure velocity of a polymer network in order to understand and infer lithium ion motion in polymer salt electrolytes. And I'll say that the work that we've been doing here, I'll put in quotes, actually, XPCS in the more traditional sense of these mixed ion electronic conductors. And in some sense, a lot of this has been driven in the quotes, I'm kind of hoping, are motivation for, you know, what are the type of things that we might want to be doing with coherent X-rays that might fall outside what I would call the typical definition of XPCS when just looking at equilibrium fluctuations, and how we apply this to systems that are heavily are very complicated. And so kind of jump into this, these mixed ion electronic conductors are a really interesting class of systems that have come about, where we actually have semiconducting functionalities. We have electronic conduction in the polymeric phase of the material, which is in both a semi-crystalline, crystalline, and amorphous states. And I'll show some examples of how varied the structures can be in these materials, where we're also simultaneously putting in a electrolyte, and we're putting ions in there, where we have to then both simultaneously conduct electrons and ions, and then actually we'll get coupling between those components as they are essentially coulombically attracted to each other. And one of the things that's really remarkable about these materials is, from a functional perspective, you can tune their energy levels and their conductivity and make devices like sensors and transistors, neuromorphics, and biological interfaces. But on top of it, we're getting radical changes in volume expansion, modulus, color, in addition to their conductivity. Fundamentally, all of these properties are tied to their morphology, and that's really what matters. And the problem is incredibly complex. So really the key, at least in my opinion, sorry. Oh, okay, sorry. Sunny, I think your mic's on. Okay. So the key here, at least in my estimation, has been really self-consistency between the electronic, the optical, and the structural characterization. And I'm really fortunate to have a bunch of great collaborators I've been working with, particularly in this area, sort of continuing this type of work with Jonathan Rivney and Alberto Soleo and their students. And this work in particular has been with Brian Paulson, Ray Hung, and Dallara. And all of the XPCS work, I would say, has been taken by Ray Hung and Dallara. And I actually had to work all of this remotely due to COVID travel restrictions. But I think it's really an incredible, incredibly grateful both. And also I think it's an incredible accomplishment. And I have to also point out just the tremendous work that the Sector 8 team has done over the past, 3 years in incredibly difficult circumstances. These are exceptionally demanding experiments and they've gone really above and beyond to make things work. I'm indebted. And I'll kind of touch a little bit on some of the stuff that I've done, particularly in the EM just to kind of give some context. And then, of course, there have been a number of other kind of follow-up studies and some of the work that we've done there. So this is the obligatory, I would say, GIWAXS introduction slide, and this is probably the wrong audience to give it to, but I'll give it nonetheless and just say that Grazing-incidence does give us a really great opportunity to get what I'll call a snapshot of reciprocal space in these type of complex materials. And it does this by giving us effectively a path length increase in some favorable sort of geometry in order to look at the scattering wave vectors. And so we can start looking at how polymer conformation along these different self-assembled structures is varying, particularly with its respect to the substrate. And to kind of give an example of just, you know, I will call it maybe the modern workflow of what we're doing, or I should say ideal workflow of what we're doing, is we're kind of using these grazing incidence techniques to get this snapshot. And then just to point out also, you know, if we think about the context of things like free electron lasers, we can go and get sort of similar structural information in sort of single shot modes in transmission as well. I think that's just something important to keep in mind as we move forward and trying to understand the advantages of the relative techniques. And then kind of bridging this into what we get with sort of localized analysis based off of, in this case, these are wavelet decomposition methods in order to look at the local structure and the correlations thereof of the local structure. In this case, this is a particularly challenging sample where I would say the majority of people would look at this and say that it's noise, but if you look at it long enough for many, many years, especially if you look at true random thermal fluctuations generated by the type of systems a lot of us study, you actually find out that it's not. And there's a lot of complex structure within these materials. And we can go through and segment them up and create local reconstructions and start doing things like analyzing domain size distributions along with adjacency of domains, looking for what I'll call higher order correlations in these materials. For example, in this particular material, there's a peak actually at around 20 degrees that corresponds to effectively an actual structural feature that is, it's not quite an epitaxial feature or homoepitaxial feature, but it's close. And then in the same sort of vein, we can use these sort of localized structural analysis techniques like sort of scanning nanodiffraction. This is some work I used to do, or I still do, looking at sort of using 2 nanometer electron beams to map out the spatial structure and then reconstruct it into orientation maps, along with subsequent analysis where we do things like charge simulations based off of these sort of real space maps. So with the kind of future of this, and I'll just say kind of coming back, if we understand all of the correlations in our data, it actually turns out you can kind of create synthetic data that actually utilizes and represents these correlations. And you could call this, for example, deep faking of morphology, utilizing higher order correlations across space and angle. So this is maybe a something to keep in mind just in the future. That's somewhat horrifying, but it's also really exciting that we can start to capture these things in sort of finite coefficients. And I think actually the lesson of being able to look for higher order correlations, particularly in coherent scattering data, has a lot of potential in the future. And that's something I'm really excited about, particularly in materials where the structure of the speckles is, you know, far from ideal. So coming back to this now, coming into the OMEC system, I'm going to talk about some of the operando work that we started with and the wide angle regime using, I'm just going to say an adaptation of one of Chris Chidsey's cells from Stanford to make it X-ray compatible. It's actually a really great cell, very simple cell for doing operando X-ray work, where we take a thin film and we press a sharpened cone similar to a conflat flange against the substrate. And this gives us a really wonderful way of actually defining the area of our sample, making electrical contact, and preventing, for example, other type of electrodes and electrical contacts from coming in contact to the electrolyte and poisoning the actual electrochemistry of the system. So we get X-ray compatibility, and we also get very high quality electrochemistry. And you know, this cell, it turns out, is okay for grazing incidence. It was a really good start, I will say, back in 2020. We've made a lot of progress since then. A lot of it was also done at Sector 8, along with here at SSRL. But it's really great for GISAXS and Grazing-incidence XPCS because it allows us to create a very rigid assembly from a thin film cell and bring in the X-rays. And the broad electrolyte background that we have in wide angle X-ray scattering essentially is not really a big issue for small angle scattering because liquids generally don't have a lot of, or most of the scattering from the liquid is compressibility fluctuations, and those are relatively small. So the other thing here to just highlight is that the OMEX can swell by more than 50% just in contact with water. So there's really not much option of doing ex situ characterization. You can do it, but you have to be extraordinarily careful, and you can make a lot of mistakes if you're not careful. So we were able to take these cells, combined with our sort of precision electrochemistry, and we were able to do these experiments at the wide angle beamline at sector 8 with Joe. And we were able to sort of go through and do various pulsing schemes and look at the structural responses of those things. So for example, we're able to go and look at the change in the measured D-spacing along with all of the diffuse structure that happens sort of at lower Q. Although at the time, I think we didn't really know what to make of that. Although I think now we have some more ideas about the context. And what's been really great about working with these groups, and the thing I really want to highlight here, is that we need complementary characterization to really start putting in the context of what the structural measurements give us relative to all of the other properties of these devices. And in this particular case, when we go from 0 volts to minus 0.6 volts, which we call de-doping, so we had a charge that was on the polymer backbone, and then we sort of removed it or did as much as we can. We can't fully de-dope these particular materials. What we find out is that the integrated charge matches the optical absorption quite well, at least for the pi star, so some intermolecular coupling transitions. However, that doesn't actually match the lamellar contraction that we observe in the material, or the lamellar changes that we observe in the material. And it also doesn't track the polaron absorption features, which are a different set of properties related to that charge on the polymer itself. And it turns out that the redoping process actually is markedly different. Particularly the polaron absorption feature doesn't seem to match, although we can argue whether or not the lamellar is now matching something closer to what these other optical absorption schemes give us. And this really kind of like set the scene for what we wanted to do with XPCS in a large extent. I will say that, you know, in the past couple of years, we've been doing a bunch of stuff really with a new schematic for a program that I hope will be relatively productive at Sector 9, although this doesn't use the coherence properties of the beamline. But we've effectively removed the electrolyte, or I should say, flipped around the sample environment such that we could put the OMEX in contact with liquid, but use a substrate with controlled scattering properties to effectively move the scattering and prevent X-rays from seeing the electrolyte at all. And what we keep finding in basically all of these materials is just an incredible array of responses. And it's really kind of been surprising to me, even though things like electron microscopy have shown me just radical differences. It's been remarkable how different the properties of all of these materials has been. So coming to this question of why use XPCS, so we started with these cone cell results of acid crystallized PSS, and we kind of had some basic questions. So the most obvious one is what do the intrinsic dynamics of these systems look like at fixed chemical potentials? So really, what can we learn about how the system as it explores its free energy landscape? Is it a really compact gel that's sort of, you know, wobbling around? Or are we seeing structural distortions from the polaronic species as they're dragging their solvation shells around? And that's a completely unknown question in these materials, although, you know, the previous work we did in solid state ion conductors will sort of let you guess what that answer might be. The other one that I think is really critical is what happens if we take a dope system, de-dope it, and redope it? Does it return back to its actual original microstate? So are there hysteresis loops as we explore the energetic landscape, as we move this chemical potential around? What's happening? Particularly as a function of rate, if we do this quickly or slowly. And then what is the role of the electrochemically induced strain as we uptake these ions? So for example, I've told you that the material can absorb, you know, 50% when it's in contact with water and ions. As you're putting in more ions or removing them, it will expand and contract, typically by a smaller amount. But these type of complications, you know, may make you think that XPCS wouldn't actually be applicable, or, you know, it may actually be something you want to measure just directly. So I'll give my extremely oversimplified view of XPCS that I would give to a non-expert. And really what it is that we're trying to use coherent patterns as a fingerprint of a system state rather than, and then try and understand how it transitions between different microstates, because we effectively can look and define an equality based on correlation matrix of a correlation that tells us when we're transitioning between different microstates. So this is, of course, the situation we're all familiar with incoherent X-rays. This isn't all that easy, if it is at all possible. And the way I always like to say it, although it makes I think Hans, my old collaborator, kind of cringe, is that every speckle is sort of an independent reporter of the state. So effectively, if you have 1 million pixels, you're going to be, you have a lot of sensitivity for looking for small structural transition. The other one that it's here, and I got to say, it was really pioneered by, oh wow, I'm blanking on the name. It's on the next 2 slides, but is looking
Mark
at
Sutton.
strain. Mark Sutton,
Yeah.
thank you. I feel a little embarrassing for that. A lot of this work's based off Mark's work, so that's a little embarrassing. So strain is a really simple thing to measure when you have a coherent lattice and you apply a strain. We get a really simple change of the bulk despacing. However, if we're applying a small strain and we have an amorphous system, this isn't necessarily true until we get to an appreciable strain or something more complex happens. But in a coherent measurement, to first order under small deformations or under other conditions, this deformation results in a scaling of the speckle pattern proportional to that strain. So that's what we're going to kind of use here to play around with things, and that's going to be important. So this is, I think many of us are familiar with what coherent scattering actually looks like. You're getting 0, 1, or 2, or 3 counts typically in the region that you're looking at. Shown here a perspective view of the cell, and we're going to start off with looking at P.PSS in water with 100 millimolar of sodium chloride. And something important, I'll put the time series up, and I'm not expecting anybody to necessarily be able to see anything in here. I just wanted to highlight again that this is, a very noisy system. And what we're looking at now is actually computing the localized strain by averaging a few seconds of images, and then sort of estimating the effective strain that's induced by the material. And this is, to me, a really amazing opportunity as an alternative to reflectivity in complex systems that are rough. And then, of course, something else that I think we all know is that with XPCS, damage is an absolutely huge problem. Being able to change energy, I think, is going to be just a real game changer. And the improved coherence should just, of course, be much, much better. So I'm looking forward to the APS-U upgrade. So kind of coming back to these pulsed experiments, we did sort of 2 sets of experiments with sodium chloride. We did these large pulses where we have a current that typically responds on the order of sort of 10 seconds. And so you get these large transients that quickly relax. And then we approximated something closer to a cyclic voltammetry curve composed out of small steps. And we took XPCS along the way. I'm going to be referring to the d-dope state. Something to keep in mind is that these are actually neutral chains with polarons. This material cannot be fully d-doped. The 0 volt is actually a lot of polarons with even some bipolar. So you can think about it as polarons everywhere with actually some bipolarons, and overdoped is primarily bipolarons. And bipolarons are just having 2 charges on the polymer and then having to coordinate 2 ions from solution. And I will say that I think that leads to some really remarkable behavior that is really not well understood. So if we actually go through and look at the strain that comes out of these materials, what we find out is that the strain is kind of coming out on the order of a fraction of a %. And it's not actually particularly reproducible. There's some break-in periods. I won't dwell too much on the strain here, other than to say that this has significant consequences for the XPCS correlation functions, which I'll address shortly. But I do want to say, if we go back and we take this strain data and we start looking particularly these large step materials, and we start overlaying this again on this complementary characterization, we've also, or I should say Rayhong has also in the meantime done some really incredible work looking at EQCM to look at the mass uptake of these materials. And we can start putting all of these together on these plots. And the main thing that I just want to point out is that the intensity change we observe with the scattering follows the integrated charge quite well, which is somewhat good. It's, you know, I wouldn't say it's obvious that that should happen, but it's nice that it happens. But the strain shift shows features that are actually, I would say, closer to what we see in the polaron absorption, although not exactly there. And the strain also doesn't exactly correspond to the strain shift or the mass uptake, but that's a subtlety for maybe another time. So I've told you that the sample itself is actually expanding and contracting, and this film thickness is changing. So how are we going to deal with that with two-time correlation function? It turns out very practically, you could ignore it if you wanted to, but that will lead to, I would call it, it's not technically an artificial change of your correlation times, but it is certainly going to be something that affects your correlation measurements. So what we've done is we've done it both ways, but we've basically created what we call a strain corrected definition of the correlation function that remaps the Q maps based off the estimated strain. So effectively, we are numerically unstraining the material to try and remove that component of it. And this is by no means a complete extraction of the information that's in there, but this is what we've been able to get with the data we have. But it is, in some sense, useful. And then what we do now is we're going to go through and we're going to start changing the strain and looking at the two-time correlation functions. And what I've done here is I have a notation where I've sort of separated this into two states, Q and R, where the sort of two-time correlation functions are locally, I would say, near a constant, or I should say have a high degree of correlation. And then there's a transition between the two regimes. That transition is not entirely exactly in the same spot. We'll kind of see that in the next slide when we go to the large step behavior. But, you know, there's more or less a reasonable self-consistency of the correlation functions with themselves. So here, what I've done is I put lowercase for the sort of vertical axis and uppercase for the horizontal axis. That way I could sort of call out different subregions relatively easily. So if I look at Q versus Q, that corresponds to this square, and I can average over this square to get a value. And that average value over here is at least nominally consistent over here, be it a little bit smaller. And what we can also say, though, is that the off-diagonal terms between these states are different. So we see that there's a structural difference between these materials that can't be accounted for by just the simple elastic deformation of the material. This gets more complicated when we start looking at actually the large step behavior. And so this is a bit of I'll call it a complicated situation. But what we've done here is we've essentially have a pulsing sequence where we go and start from the state S, which is doped. We go to de-doped, which I'm calling T. We go back to redoped, which I'm calling S prime. Then we go to overdoped, state V, and then we go back to the doped phase. And what we see here is that if we consider, you know, S, S prime, and S double prime here are all the same chemical potential. The current transients here are on the order of 10 seconds, and we're waiting on the order of sort of about 300 seconds at each step. So we at least thought that we'd be in equilibrium. So if the material was at least reversible, we might think that going from S to T to S prime would return us to the same state. And that S prime going to V, going to S double prime would also return us to the same state. What we find out is that actually S going all the way to S double prime here, so going from this little region here where we see the most intense red, we actually have the highest correlation over here once we go back to S double prime. And so that's sort of what this implies here. So that means that somehow this path dependence is giving us some sort of, I'll call it an electrochemical hysteresis loop in the material. Additionally, we also see that we have these off diagonal terms that are kind of fading. So this is again going from S prime to S double prime. This off diagonal term is equilibrating very slowly. So this 300 seconds doesn't seem to be even remotely enough to get us into the equilibrium structure. And then again, we also have them going from S to S prime as well. And again, we're not in the equilibrium case. So there's something that's kind of profound here. It's kind of amazing that if we go through this whole hysteresis loop, that we do seem to really get back to something similar. But again, this path dependence forming polarons and bipolarons, there's something really interesting here. So all of this was done with sodium chloride. if we instead go and do something with rubidium bromide, and we do a very specific experiment where we start looking at the dynamics, particularly focusing on trying to understand as we switch states, what's happening. Rubidium bromide gives us a significant increase in the contrast just from the atomic number. And what we're trying to understand now is essentially what are these processes that are happening during the transient, in addition to the equilibrium dynamics and how long it takes to get there. So if we go from the dope state down to the de-dope state, so we go from a lot of polarons with a few bipolarons, basically down to a fully just neutral and polaron state, we see that there's actually an intrinsic time scale there in the system on the order of a few hundred seconds. And we see that we actually get there almost immediately when we de-dope. There's essentially no transient time. And you can see that by how sharp this sort of inset here is in the corner immediately after the transition. And sort of the simple theory that we're going to talk about on the next slide, this is the sort of shape that you would get from the correlation function. But when we go upon redoping, we actually begin to see a marked change in this behavior. So if we start in this de-dope state and we go and form to this dope state, this redope state, where we have bipolarons and polarons, we actually see what looks to be something that follows a dynamic scaling law, where we have some sort of short induction period that is on the order maybe of the current transient, albeit maybe a little bit longer. And then we see these scaling laws that come afterwards. And sort of following the sort of dynamic scaling law model and fitting and these are some sort of examples of fits, we end up essentially getting a growth exponent corresponding to 3, which corresponds to the sort of model B system of the Langevin system, sort of implying that we have at least a conserved order parameter, which is in some sense like a kind of a sensible thing. You have polaronic species where you have single charges, and then you have higher order charge species, what we're calling bipolarons. And most likely what we have is a system where we're actually getting a coarsening process that's happening during this transient. And in fact, we never even got to the end of it to see it actually see, what the true timescale for equilibrium, but extrapolating that on the order of 500 seconds, which again is about 50 times larger than the current transient. So coming back then to the type of physics that, it might be telling us is happening in these materials, I'm not going to say that this is, I'm definitely not an expert in this, but as far as I can tell, the best sort of theoretical fit for what's happening is this idea of sort of the chemical kinetics and charge transfer based off of non-equilibrium thermodynamics from Martin Besant, and in particular talking about this sort of heterogeneous chemistry where we have a locally conserved order parameter and the reaction is taking place particularly at the interface of the domains. And sort of just kind of to show kind of schematically coming back to the sort of TEM models, this is of not P.PSS, but just of a different material for just to show schematically. These white lines represent the neutral chains. In the de-dope state, I'm going to just say that we have these sort of domains of polaron species as we're never fully de-doped. And what's happening is these are actually diffusing around in time. So they're maybe moving around. And this is that intrinsic time scale that we're sort of measuring is the structural deformation of the material as the polaron is dragging this around, even in thermal equilibrium, which is itself a remarkable concept in these materials that's not widely appreciated. We naively think in a semiconductor that, the electronic, carriers are diffusing. People in these materials generally don't think of the ionic components diffusing structurally. As we go into this redoping phase, effectively, we have all this excess chemical potential energy, which means that we can activate pretty much any site at random through the film because of the overpotential. And so what we're going to do is we're actually going to form polarons in a lot of places and potentially even bipolarons and an excess of bipolarons as well. And what will happen sort of then immediately during that transient is some of those bipolarons are going to decay into polarons, and then we're going to kind of fill up polarons everywhere we can because they're presumably a lower energy state. And then effectively, we're going to see the structural coarsening and then subsequent evolution of these materials as they go. And then in equilibrium, we're seeing, so somehow we're seeing this combination, what we think is that. So the consequences of this are, we're still trying to figure that out. I mean, first of all, it just means that a lot of times people are operating these materials. They watch the current decay, The reality is we're in a completely non-equilibrium state as far as the material is concerned. So we don't understand the consequences of that. There's also some interest, in the idea that you could engineer the sort of criticality and the fluctuations of these materials to achieve sort of novel functionality. And by controlling these non-equilibrium states, particularly, in generating and creating new things by, for example, adding different salts or multivalent salts, where the competition between these would produce new behavior. And then how this actually affects device scaling is, I'll say, concerning as well, because it also implies that those carriers are mobile. And so that's just something important. And with that, I'll really thank the people that, made this work happen. Everyone at Sector 9, the Rivne group, and it's a lot of help engineering these cells on the SSRL side as well, people I work with. With that, I'll ask for any questions.
Thank you, Chris, for a great talk. Questions from anybody for Chris? Please just go ahead and unmute and ask your question if you like.
Hi, this is Hua. I have a general question for the last part of the model. So you're thinking the dynamics for XPCS observation is some kind of like a polaron by polaron. They're induced some strain effect in this polymer film, which can pick up by XPCS. Is that right? Or the time scale is have you need to do some conversion? Is that really the time scale you observe on XPCS is really equivalent to the time scale for the real polaron, propagation, or their transformation, or there's some scale factor, or this is just exactly the same time scale?
I would say I don't have enough information to say that exactly. So I do think it's actually primarily the polaron structural distortion, and that what we're seeing is the bipolaron mediating those interactions and changing them or driving them. That being said, what the actual time scale is for self-diffusion of the polaron species, I don't know. It could be that time scale, but unfortunately, we were not able to measure, for example, the Q dependence, or do something even fancier, which would be like looking at whether it's ballistic or something like that, and actually being able to fit those sort of Q dependence. And we just didn't have the signal to noise to do.
I see. Thank you.
More questions?
Yeah, I have a couple of questions for both speakers. So where should I start? Maybe Chris first.
Sure.
So if so you showed that movie with the speckles, is that under relaxation, or these are in the stress, so that
That was during the electrochemical experiment. I believe that one, and Ray Hunt can correct me if I'm wrong, that was during one of the cycling experiments.
Okay, yeah.
Or it could have been the transient stuff, but yeah.
Yeah, those transient stuff. So actually, if Chinton, I don't know if Chinton is around. So we did the similar experiments with the in the real space, not in the. I assume this is in the reciprocal space. You see the speckles like this, right? It's a, and so Chinton helped us to do these, the transient or time-resolved correlation analysis, and those things turns out to be pretty nice, so that if Chinton around, he might give you, might have a more, comments on this. And the other question I have is that these polarons. So what is the length scale of those, of the polarons? These are, or the correlation length of?
So the actual scale of polaron, I would say, isn't particularly well characterized. It's likely at least a few nanometers, although the extent to which that propagates is, the structural distortion around that, how far that goes, could be a little bit longer.
Okay.
Yeah. So this is some sort of collective mode, most likely, or I should say collective in the sense that it's a collection of the structural distortion. Unfortunately, we also couldn't quite get data to go after and look at how this also changed with I of Q. But the other thing to consider also is that these samples are pretty messy. So there's actually other likely things happening that are not necessarily related just to the time dynamics of the system, but there are other structural transformations inside. The time dynamics are just kind of on top of that.
Okay. So it's hard to separate the contributions from them, Yeah.
I mean, I think the dynamics actually do a pretty good job of that. I mean, I think that's kind of the really surprising part, is that we're able to kind of, in some sense, disentangle them.
Okay. Great. Thanks, Chris.
Thanks. And also, Chris, in case you need any information about the real space spectral tracing, we can talk a little bit more.
So Chintan, I hope that's something, similar to, those analysis that we did, right, with these polymer starch films, so that.
Right, I have seen Rayhan's analysis, and although Rayhan speckles are in the reciprocal space and
right.
Our speckles are in the real space, but the speckle tracing part is roughly the same. So
okay, yeah, that's what I wanted to comment on, is that how to trace them, so that
yes.
Okay. So okay, I got a question for Carl. So the same two-time correlation function diagram that the Carl showed, so that so at the higher, these corners, these what do you call it, the other diagonal side of corners, then not corners, I mean edges, you'll see the the correlation actually come back. Are these real things, or these are artifacts, or?
You're talking specifically about that work I showed that's being analyzed from the plasma enhanced ALD growth?
Yes.
Well, I think you're, if I may share again, I think that, can you see my cursor?
Yes, that's what I was referring
Are you
to.
kind of talking about this kind of region in here, or
right? So that's where. So if you draw a line there, so you will see the you have a maybe a little lower, then you will see the diagonal line there. I mean, you will see what the things the correlation will decrease and coming back.
It's kind of it's a little bit hard to believe that would be the case on those time scales. Of course, again, there's this very fine time scale associated with the 60-second growth sequence, and there you certainly see correlations come and go in a very reproducible way. But one of the things I pointed out, and maybe others have better insights than we've had, is the challenges of normalizing data that's not in a stationary state. So that could be a challenge for normalization for some of these longer period things. Yeah, I don't know if anybody else has comments on normalizing such data. We've worked very hard at it, you know. But it is hard to believe some of those longer time variations. Yes.
I would say also, I mean, this is like incredibly hard. I'm actually really looking forward to potentially being able to move the samples with the type of precision you're talking about. So we can look at multiple regions of the sample and use that potentially for the renormalization of some of these behaviors.
So do you think this is something to do with the, you know, the particular sample, so that, you know, the surface is highly textured. So, you know, in addition to, you know, some kinetic effects, you know, so due to these intensity, causing these intensity fluctuations. So that
when you say textured, you mean like in a rough sense?
Yeah, the rough sense, and those are you know, not only rough, right? So that you show the images, they can be quite regular, you know. So yes, so less, you know, less regular perhaps in this kind of growth process, although there are correlated mounds.
Actually, Jin, if I remember correctly, for the nanoparticle embedded in the polymers, I guess it is more like a micron-sized particle. We have seen similar of these oscillation of the correlation, in which a correlation comes back at the longer term. So at a higher frame rate, you'll be able to see these checkerboard pattern in the two-time correlation function. And actually, Suresh and Eric have seen similar things when we were at ESRF, and we look at the relaxation of these gem nanoparticles. So I think the coming back of the recovery of the correlation can be real. It depends on what type of system you're looking at. Some of the systems, because of its intrinsic elasticity, there's some possibility that the correlation could resume in very short time durations.
So is that the case that you're describing, you think, that you're seeing longer term return of correlations due to, you think it's a sample effect versus scattering?
That's a great question. So in our case, all the recovery of the correlation happened at shorter time scales. So over the longer time, the entire correlation still decay, but within very short duration. For example, if you run at say like a 10 hertz or 50 hertz for tens of seconds, eventually at the longer delay time, all the correlation diminishes. But if you zoom in with 10 kilohertz at very short, within the very short duration, then at the fast time scales, there are some oscillation of what I would guess is probably microstructures. So there are oscillation of these structures.
And do you have physical rationale for that?
In Jin's sample, if I recall, this what Jin and collaborators from UChicago are working on are these micron-size particles embedded in more like a polymer matrix. And when you stretch it, there is overall relaxation on the macroscopic scale. But our guess is as you stretch the medium, there is jamming of the nanoparticles, and some of these nanoparticles have local oscillation that happen more like the particle interparticle spacing scale. So that would be our guess as to why there is more rapid oscillation of the correlation. And in Suresh cases, the nanoparticles is a lot smaller. We're talking about something that's between 100 and 200 nanometer diameter, and it's something that when you shear it into a very high far from equilibrium state, and then it relaxes. So there might be oscillation as a system is jumping between different metastable states. But regarding that,
one thing is that this is a much longer scale, and the sample, you know, it's hard to think the sample has a or to fall into this kind of a length scale. So, but we can talk more about this in the future, so that I think it's pretty interesting stuff. But one more thing for Carl is that so you're talking about I would say would be the last person I would expect to talk about the a radiation damage on these systems. So that so I assume you saw these the signature of that at the NSLS, right? So that sorry, NSLS 2. So so it'll be interesting to hear more about it, so that when we get a chance, So.
Yeah, I think so far we've been pretty fortunate. Of course, we're looking at hard materials, but one would have to sort, people would be asking questions, right? This is a PEALD growth process, right? You're putting precursors down, right? People would probably be within their rights to ask, what's the effect on those precursors of these intense X-rays? Although we do correlate, of course, with non-X-ray studies and find good correlations. So, yeah, it is ultimately something we have to be very careful with.
Okay.
That's
Thank you.
encouraging. I see questions from someone who hasn't had a chance to ask yet. So next question from Po Chun Soo.
All right, thank you, Joe. Thank you, Chris, for the great talk. I have one quick question. So when you talk about the diffusion of polaron, was it correlated to, for example, the sodium, which is the counter ion that need to move to create this locally undoped or doped state, or is something else?
Yeah, I think so. So in that particular case, I think it was we were using rubidium bromide in those experiments. Without the rubidium bromide, it was a little bit challenging to say, not that we couldn't measure it without sodium chloride, but it was certainly much easier to measure with the rubidium bromide.
Okay, thank you.
And I see, and Hua's had a question, I think, for Carl since before.
Oh, yeah.
Since
So I
earlier.
I have a second question for, Carl is on the second part of talk. So for the polycrystal, film depositions, that was very interesting. So Carl, I think it looked like the grain size pretty big, right? It's like from AFM, it's like already, quite few micron. So I was wondering, maybe, compared to the beam size, this may not be already polycrystal, right? This is like more like a single crystal, because your beam, I don't know, or maybe Grazing-incidence, the beam size will be bigger, the footprint will be bigger, but for AFM, look like the grain size already very big. So my comments is maybe this is just single crystal growth rather than polycrystal growth, or you think the speckle still coming from like a multi-grain from the measurements?
Yeah, I think the beam was large enough; it was hitting several grains.
Several grains. Okay.
A good number of grains. So I think it's not simple. Yeah, you're right. If you focus enough, then with that size scale, maybe you can almost be single crystal. But this was definitely so there were not intensity oscillations. Okay, there were correlation oscillations, but not intensity oscillation.
Okay, but those grain have a do they have any implant texture or orientation dependent affected this result, or this is very random? Implants very random. So if it's random, probably it's not a problem.
These are ultimately these are highly textured.
Oh, okay. They are textured. They're highly textured. Okay. So okay, that's interesting to see, especially because there's I don't know, the correlation oscillation is really relevant to this step flow, but I think those steps are going to be like atomic scale, like a few angstrom. That should be very high Q you can observe. But this measurement sounds like a very low Q. I just wondering whether they can directly probing such a small, length scale stuff. So.
I'm trying to remember what the QZ was on these, but this was higher up the rod. It was not very low. I think you would have seen.
Okay. So high enough. Okay. Got it.
Yeah.
I thought it was very nice to see this polycrystalline, that although the sample was polycrystalline, it gave you such a nice kind of two-time, and it seems because there's hundreds of these things in the beam, right? There's on the order of 100 of these crystals.
Well, at least dozens, I would say, yes. And the other, I'll also come back to that other two-time correlation plot I showed from the ALD growth. There, it's also polycrystalline growth. And in there also at later time, except for the very early times, there are no, well, we never get classic intensity oscillations. There are changes in intensity associated with particular parts of a growth cycle during the early stages of the growth, but very quickly, the intensity is relatively constant, or at least changing only slowly, but yet you can see a lot of structure in the correlation function.
Okay. Well, I really appreciate everyone who's stuck around. We've gone a little over time, and I guess
Did
we should be
miss the
mindful.
question from Crystal, Joe?
I think
No.
Paul already was just slow putting down his.
Yeah, that's
Oh,
me.
that
That's
is,
me.
oh,
Sorry,
that's you.
me,
Sorry. Okay. Sorry.
So, okay, thanks for pointing it out, though. So I do appreciate everyone's energy, interest, and enthusiasm, especially staying a little over time. I think, though, we should probably wrap up, because we'll get to discuss more tomorrow when we resume at 9:45 Chicago time. But before we leave, maybe I'll just lead a non-virtual round of applause for all our speakers today. Thank you, everybody, for all your participation. I look forward to more enthusiastic discussions and great talks tomorrow. So thank you so much.
Thanks for organizing.
Thanks, everybody. I'm going to end the session now.
Thank you.
Bye-bye. Thank you.